With this video, I want to complete the thought on ideas about where accelerations are functions. So we looked at what happened when accelerations were constant. We ended up with the kinematic equations that we knew from last year and love so dearly. And we also looked at what happened when the acceleration was a function of time. No matter what, anytime the acceleration is a function, the way that we're going to attack these problems is to substitute, separate, and integrate. That's the pathway through, to substitute, separate, and integrate, bringing everything together. So far, the acceptable substitutions we know is that A is equal to dv dt. We also know that A is equal to, we look at this, ddt of x, right? In that it is the second derivative of position with respect to time. And we'll talk about that one again later. We also know that I just used this here, that v is equal to dx dt. Now, v could equal dy dt, dz dt, dr dt, whatever. I'm just going to use x as our position variable just for sake of convenience here, right? So when we had a was being a function of position, or excuse me, a function of time, all we were doing is substituting in for a what that function was, separating the dt over to both sides, or to the other side, and then integrating the function with bounds in order to come up with a new equation for velocity. Super easy there. We said that we're going to have problems when acceleration was a function of other things, like position or velocity. So we're going to talk about acceleration as a function of velocity first. Okay. And you might think to yourself, hold on a second, that doesn't sound like the easier one to do, but in fact it is. And we said that our example of when this occurred was air resistance, that the faster you go, the higher the air resistance forces. Obviously, forces affect accelerations. And so I just wanted to show you an example here of air resistance. Let's say that I knew my acceleration was equal to, well, if it's an air resistance force, that force is going to always act opposite the direction of the velocity. So if I'm moving forward, air resistance acts backwards. So I'm just going to have a negative there. And then there's going to be some sort of constant. So I'll just use B as a constant here, V. Let's just say that that's what it is. Actually, no, constant. Let's just do K for a constant here. So A equals negative KV. So there we go. So what am I going to do here? Well, let's say I want to know the velocity is a function of time and the position is a function of time. That's sort of what our goal is. Right now, I don't have times in here, so there's two ways to get time in here. I can either put dx dt in for this, but that kind of really muddies the water because then I have x's, t's, and a's, no bueno. Or I could put dv dt in here, and then I'm down to two variables. So dv dt is equal to negative kv. So let's just stop here for a second, and I want to just call this what it is. This is called a first order differential equation. Okay, first order because the highest order derivative in it is the first, because I have this dv dt, and you'll notice that all terms have a v in them. So here, first order differential equation. This particular differential equation, we're going to find it out, is separable, which means it is easily solvable. Separable means that I can get all of one variable on one side of the equality and all of the other variable on the other side of the equality. So in this case, I can get all my v's on the left and all my t's on the right. So I'm going to do that now. So dv over v equals negative k dt. Now that negative k could have come along for the ride anywhere. I'm just going to keep it on the right because the right side of this equation is simpler right now. And so I think it'll just make the work a lot nicer if I keep this on this side. So we can see that this is indeed separable. There's another word that we can use for this first order differential equation. It is homogeneous. And what that means is that all the terms are of the same type. What type is that? Well, each term, when it was in this form, had a v in it, right? There were no extra, like there was no like plus 6 here, there was no plus x squared or plus t. Every term had the same variable in it, that v variable in it. And so that's what it means for this to be homogeneous. All right, so it is a first order separable homogeneous differential equation. Anyway, let's go and solve this now, because I've substituted, I've separated, now I'm going to integrate. Now here's the thing. We're going to go from 0 to t here, and then from vi to v here, right? Because we know that this has to be, the bounds here have to be with respect to t, so we're going to start the stopwatch when we want it, up to some random t, and we know we're at an initial velocity when the time is equal to 0. Now here's the thing, this initial velocity won't be equal to 0 because it doesn't make sense, right? Because if this velocity is 0, it's not experiencing that acceleration because you only experience air resistance when you're moving, right? So there's kind of like a little fun fact there. And so what does this become? Well, the right side of this equation is super simple. That just becomes negative kt evaluated between 0 and t. The left side, as you all told me before, that's ln of v evaluated between vi and v. Now, in math class, that would be ln of absolute value v, but I'm going to leave that off because, as I know here, there are going to be some constraints upon this that kind of get me out of having to worry about stuff in there. But if we wanted to be really formal about it, I could put that absolute value sign in there if that makes you happy. But I'm not going to right now. Not that I don't want to make you happy, but it's a nicety that we don't really need for this particular problem. So if I evaluate this, I get ln of v minus ln of vi is equal to negative kt minus a minus k times 0, and that term goes away. So the goal here, remember, is to solve for v, right? So I got to get rid of that ln. So I'm going to use a log rule here because rather than move this over to the other side, I can exploit the log rules just to make my life a lot easier here. ln of v over vi is equal to negative kt, and then I can raise both sides to e. And so we know that this becomes e to the ln of v over vi is v over vi, and this is e to the negative kt. And therefore I get v is equal to vi e to the negative kt. And there you go. So what sort of form of function is that? That is an exponential decay, that if I were to graph that velocity as a function of time, it would start at some vi, and it would asymptotically approach the time axis but never quite reach it, meaning that the air resistance force can never actually stop the object. Something else will stop it. Probably it's experiencing friction simultaneously, which means that my original equation for acceleration was not actually right, but let's just pretend that the only force this thing was experiencing was the air resistance force. All right, and that's a common shape, folks. That's the e to the negative something t graph. E to the negative constant t graph, and that's something that you should get to know because that's going to come up all the time. All right? So there we go. So I've gotten v as a function of t, bravo. Now let's get, x as a function of t. Simply, all I'm going to do here is now substitute, separate, and integrate again. So v becomes dx dt, vi e to the negative kt. dx is equal to vi e to the negative kt dt. Integrate, and I'm going to go from, once again, 0 to t, and this is from xi to x. Simply enough, the left side integrates into x from xi to x, and here this is going to be vi over negative k e to the negative kt between 0 and t. And if you want to see that a little bit more formally, I would have to let u equal negative kt. I know du dt here would be equal to negative k. du is equal to negative k dt, meaning when I would go back and do that substitution, I would have vi e to the u dt. I'd have to multiply by negative k over negative k. There's that term, and I've got vi e to the u over negative k du. Obviously, that's a constant, so that pulls through the integral. And I've just got e to the u with respect to u, which is e to the u, and e to the u is e to the negative kt, so there you go. Okay, so x minus xi over here is equal to v negative VI over K e to the negative KT minus negative VI K e to the 0. Now this is why, folks, I've been stressing always evaluate the lower bound, because this lower bound is not going to go to 0. It is absolutely not going to go to 0 because e to the 0 is not 0. It is in fact 1. So what do I have here? I have x minus xi is equal to negative VIK e to the negative KT minus, so plus a VIK. Let's order this nicely. X is equal to xi, do this term next, plus VIK minus VI over K e to the negative KT. All right, so that graph is going to have the same sort of look to it, except that, let me just organize this a little bit differently. Xi is equal to, or the xi plus, I can factor out that VI over K, and I have 1 minus e to the negative KT now. This is another graph that I'm going to want you to know. The 1 minus e to the negative KT graph, well, let's see what happens here. If x is equal to, or rather, if t is equal to 0, I have e to the 0, so this term zeroes out. That means that I start at whatever the starting position is, whatever xi is, okay? But then, if we look at this, as t approaches infinity, that term goes to 0, and this term approaches some sort of constant. So there's some sort of horizontal asymptote here that would be xi plus vi over k, okay? And so this graph does this. So this graph is the 1 minus e to the negative kt graph, this sort of thing with a horizontal asymptote that is above the axis. And that is another popular graph that comes up over and over and over again in physics, and something that you should be conscious of and aware of and be looking for. So there you go. We have now fully explored this. Now, this is a very boring problem because the original function was pretty easy, where a was equal to negative negative kv, right? But what happens is equal to, a is equal to, I don't know, v squared, v cubed, the square root of v, the ln of v, whatever. The methodology doesn't change. It's just substitute, separate, and integrate, substitute, separate, and integrate. It's just the integral gets nastier. That's really all it comes down to. All right, so cool. Let's go on to the next one, where we're going to talk about the acceleration as a function of position. And this is a really important one for physics. Because there are so many forces that are functions of position. In fact, all of our fundamental forces are functions of position, meaning this integration process is going to come up all the time. And this one yields some really, really nasty integrals. There's just no way around it. That's why a lot of these weird integration techniques that you learn in BC Calculus were created, was to solve these problems. Now, we're not going to start out nasty. We're going to start out simple. The force that I know that has the simplest expression that is a function of position is the spring force, which is negative kx, if you remember that. Meaning if I displace the thing to the right of the equilibrium position, that the spring force is to the left of the equilibrium position, pulling it back to the equilibrium position, and vice versa. Let's say that this is the spring force is the only force acting on an object. I don't know how that is, but let's say that that's a true thing. And I displace this thing to the side, and then it would just, like, you know, what would it do? It would oscillate back and forth. But if it's the only force that's acting on this, well, then the spring force is acting as our net force. And if you remember, F net is equal to ma vector vector. We'll go over that when we get to chapter 5, but you should know Newton's second law already. And so if the spring force is the net force acting on this, in place of this is just a placeholder for the vector sum of all the forces. I can just put in negative kx as being the force. All right, so here we go. So now I've got this expression. Once again, I'm looking for v is a function of t and x is a function of t, and so it seems logical that I would try and do some substitutions here. So negative kx is equal to m dv dt. And we looked at this before and we said, no, 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 nope, this is no good because what do I have here? I have v's, t's, and x's. I have 3 variables. Okay, 3 variables mean this is not separable. Okay, not separable. So no bueno, I can't solve this. So going back now, the other one I have is I know that I can replace a with d squared x dt squared, the second derivative. So now let's look at this. What do I have here? Well, what I have here is something that is called a second order differential equation. Okay, second order because the highest order derivative in the expression is a derivative of order 2. Now, you will also notice that this is homogeneous if you remember that definition from before, because notice all the terms here have x's in them. There's no constants, there's nothing else. Every term features an x. Then what we have to understand is all second order differential equations are not separable. Because unlike dv dt, where dv is a little change in v and dt is a little change in t, d squared x is not a thing. dt squared, well, that is actually a little change in t squared, but that's not really a thing either. Like physically, it's not really a thing. So this is not separable. So what do we do with it? Well, we'll come back to this because we can actually solve this, believe it or not. We just have to be a little bit more clever. What I do want to do is I want to take a moment to put this in its proper order. So if you end up taking the AP exam, they're going to ask you to write the differential equation that can be used to solve. And so when you have a differential equation, the proper format for the differential equation should be setting equal to 0. And then what I'm going to do here is I'm going to order the terms in order of decreasing derivatives, right? Pretty easy. In this case, I only have the 1, right? And you'll notice there I move the m out in front of the first term, because generally when you write a second order differential equation, you try and keep this as 1, right? If we're doing our normal problem. And this is the general form of a differential equation. So if I'm actually talking about what is the general form of a second order homogeneous differential equation, it's d squared, whatever variable, dt squared, right? Let's say we have x in this case, plus, and then we just say p times dx dt, right? Plus q times x, right? And so here the q is k over m, the p is equal to 0, and then we don't have to worry about that. But that's the general form of the second order differential equation when written in proper format. That should look kind of familiar, but we'll come back to that in a notion a little bit later. But right now, from the math that you know, that is not solvable. I wonder if there's another appropriate substitution, because so far we've tried a is equal to dv dt, and we've tried a is equal to d squared x dt squared. Now, when things don't look the way that we need them to look, there's oftentimes something that we can do. And hopefully you've just said to yourself, chain rule. Because that's right. What I can do here is I can turn this into a little bit of a chain rule. dv dt, as long as this is the same thing, I'm good to go. And so because what I have here are x's, I'm going to use a dx dx. And if you look at this now, dx dt, that's just v. So a is also equal to v dv dx. And there's our third substitution for a. And that's a good one. It's going to come up quite often. So a is equal to v dv dx, which is just kind of fun to say. A is equal to v dv dx. So let's use that substitution in this case. Okay, so I've got negative kx is equal to m v dv dx. Now the nice thing about that is we look at that, it's a first order equation, and it is separable. This thing is not quite homogeneous because there's no one thing that's in all the terms. But we're not going to get too bent out of shape. That doesn't mean it's not solvable because it's separable. I can very simply move this dx to both sides, and I've got that. And then I can integrate both sides. Now here's the weird thing. We have no t here, so I can just go from vi, this would be xi, and this is v, and this is x. So at least they're contemporary. They're both functions of t. X is a function of t, and v is a function of t, and so we can say at the initial and at the final, right? This is a nice simple antiderivative, so negative 1/2 kx squared evaluated between xi and x, and this becomes 1/2 mv squared between vi and v, all right? And so we can then say negative 1/2 kx squared. Oh no, I'm running out of ink. I'm out of ink there. X squared minus a minus 1/2 kxi squared, okay, is equal to 1/2 mv squared minus 1/2 mvi squared. And so if you're looking at that, you're saying to yourself, gosh, those are familiar terms. Those are really familiar. Like, I've seen those before in my study of physics. Anyone know what those terms are? Hopefully you're saying to yourself, hold on, I know this. Kinetic energy is equal to 1/2 mv squared. Hold on, I know that. The potential energy of a spring is 1/2 kx squared. What on earth do I have here? Well, it looks like I have, well, let's just clean this up with some negative signs here. This is the potential energy of the spring finally, minus minus a plus, and this is the potential energy of the spring initially, is equal to the kinetic energy finally minus the kinetic energy initially, or if we just move things around, I don't like negative signs. So kinetic energy initial plus potential energy of the spring initial is equal to kinetic energy final plus potential energy of the spring final. Hold on a second, what on earth is that? That is the law of conservation of energy. What? So the law of conservation of energy is a consequence of calculus? Yes, yes it is. Now, that doesn't help us solve a problem. It's just something kind of fun and neat. How on earth could I solve this problem? Well, you're not going to like it, and we're not going to do it because that's just going to get into the weeds. But if you notice here, I can solve this equation for v as a function of x. And that would look like moving everything over onto this side. So I would have 1/2 mv squared is equal to 1/2 mvi squared, and then plus 1/2 kxi squared minus 1/2 kx squared, right? This is just a big old constant, folks. So I could just replace it with c or something if I was going to do the next step of this. But then I can solve this for v, right? So just divide through by m, and the 1/2 divide pretty easily, right? Divide through by m, so I've got v squared is equal to vi squared plus k over m xi squared minus k over m x squared. And then I could take the square root, and then in place of v, I could put dx dt. And then I have x's and t's, and then I could separate and I could integrate. And that integral, let me tell you, is nasty. Nasty, 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 nasty. So we're not going to focus on it now, but certainly that is a solution. And then once I have x as a function of t, I can take the derivative of that and get v as a function of t. So nice and simple. Not really simple, but it's doable. It's doable. Let's just call it that. But what I want to go back to is the notion of our second order homogeneous differential equation. Because I want to spend a little time on this. So I've got negative kx is equal to m d squared x dt squared. So what does that equation say? It says there exists a function whose second derivative is the negative of itself times a constant. Okay? Or if you want to look at it in this form here, right? If I need this to come out to be 0, whatever function I put in there, this function needs to be negative of the same function so that the equality goes away and this constant k over m needs to pop out. Geez, like what on earth would have this attribute? Oh, we know a couple of functions. So stop and think for a second. And hopefully what you said to yourself is the sine function or the cosine function, right? So let's look at both, make sure we can get this work. I'll just pick cosine for no reason. Cosine of, and it would be cosine of t, right? Because if I do the first derivative there, I get negative sine of t. And if I do the second derivative there, I get negative cosine of t. And so if I were to plug that in now, I would not, it wouldn't work, right? Because I wouldn't get the same thing on both sides. So negative k, and then here, actually, let's go to the other version of it. D squared x dt squared, this has to all equal 0, plus k over mx, right? Here we have 0 is equal to, question mark, negative cosine of t plus k over m cosine of t, right? It's so close, so close. I would need a k over m to pop out there. So how would I do that? How would I make this have a negative k over m in it? Well, hopefully what you figured out is then I need to alter this original function. I need a k over m in there. So what I hope you'll remember is if I have x is equal to, I don't know, say cosine of 2t, that dx dt would be negative 2 sine of 2t. The periodicity doesn't change, and the constant pops out. And then d squared x dt squared would be, it would pop out again, negative 4 cosine of 2t. The periodicity doesn't change. So whatever is here is going to pop out twice. So if I make this radical k over m, this becomes radical k over m negative, and this is radical k over m. And then a second radical k over m pops out, making this k over m, negative sign, radical k over m. And there we go. That, when I plug it into here, would give us 0 is equal to negative k over m cosine of radical k over mt plus k over m, and then the original function cosine of radical k over mt, and that would in fact equal 0. And so this is a valid solution to this equation. So would it, by the way, if I just multiply by some constant here up top, right? That would work as well, because then this would also have that a term in it. And the same thing would work as well as if this was sine, right? Because, I mean, that should make sense because the cosine and the sine are just like 90-degree shifts of one another. So if one is a solution, the other might be a solution as well. So that is a solution to this second-order differential equation. Now, there wasn't a very formal way I did that. What I did was I guessed and checked. I knew something about what the answer had to look like, and then used my knowledge of mathematics in order to solve. Now, that's not a very efficient way of solving problems, but for the moment being, that's how you can solve a second-order differential equation, is with asking yourself, well, what has to be the format of the answer such that that you get a solution that works? Now, I'm just going to preface this for something we're going to do much later. If you look at this, what does it remind you of? And if you said to yourself a quadratic equation, you're right. That there's a way of solving second-order homogeneous differential equations much in the same way that you would solve a quadratic equation. And it's really a neat thing. Okay, so what do you have to know for this? Kind of went into the rabbit hole here a little bit, but it's super interesting. You have to know the 3 different substitutions for a: dv dt, d squared x dt squared, v dv dx. You have to know the substitution for v as being dx dt. You have to know how to substitute, separate, and integrate when you have accelerations as a function of position and accelerations as a function of velocity. If I ask you, write the first order differential equation that would be used to solve, you need to know what that means. If I say, write the second order differential equation that could be used to solve, you need to know what that means. At this point, I'm not going to expect you to be able to solve second order differential equations like this, like I was just talking about, but I did want you to think about that, mostly because look at that answer. This says the position is a function of the cosine. So in other words, it's oscillating. Remember what our system was. We had our system here, which is a mass and a spring. And what does the mass on the spring do? It oscillates back and forth. And apparently, its position oscillates as a cosine wave or a sine wave, depending on the initial condition. But we're going to come back to that because, folks, that is chapter 13. But I just wanted to preface it now since we're doing substitute, separate, and integrate.